All right, we are now kind of in a weird environment. Rather than being on Facebook, we're in YouTube. I'm going to check with our guy and make sure I can transfer this link over to him on Facebook, and we'll just do it that way.
Okay.
Let's a couple of things to make sure of here is let's go to. I'm going to hop over to Facebook and. Yeah. And we'll get that. This is going to be weird for a second. All right. So I think this is going to work. Gerard, thanks for being patient with me. I'm waiting on our guy here just to. Apparently, it's a Facebook issue.
Okay. It's fine. I've ordered some bottle jacks, sent a paper to a colleague, and now I'm registering to donate some blood.
So you can still hear me, correct? So the one weird thing about this is I had to make sure I was muted there, because otherwise you get that double. You hear me over and over.
Yeah. Mm-hmm.
And okay, so that actually should work. And so I'm going to go ahead and again apologize to everyone. Jim will be directing you over to our my YouTube site. I'm using my my personal channel here to direct things out to you this evening. It looks like there was a little bit of a Facebook connection issue tonight. Who knows? Here it could be the weather. It could be anything. So I'm going to just briefly introduce here the gentleman with me, who's Dr. Gerard Van Bael from the Lowell Observatory in Flagstaff, Arizona. And it's not a, I know it's warm and probably dry and everything out there, but here in the Atlanta area, it is it's a stormy evening, kind of typical late afternoon overcast. So not a great time to look at those stars. So it is a time when we can, when normally we'd be fortunate to go inside the planetarium to be able to enjoy the night sky. And instead of our large 71-foot diameter dome, we have to rely on some programming here to, like Stellarium, to take a look at the evening. And so I'm going to go over here just for a moment to point out a few of the highlights for our audience. And of course, we're looking south here, and I like moving around to the west to show you the, the sky as it is right now. Here, a little approaching 7:30 in the evening with the sun still up. So we want advanced time so that we could see those stars other than our own sun. And to do that, we'll advance here to about 9:30 or so tonight, close to 10 o'clock. And as we look out to the west, probably what you want to do is direct your eyes upward a bit, and you will see the 7 stars that make the pan and the handle of the Big Dipper. Sometimes people are surprised when we point out that the Big Dipper is not a constellation. It is an asterism, which is just a fancy name for a shape made of stars. And like some asterisms, not all, but some, the Big Dipper is part of a constellation called Ursa Major, the Great Bear. And it's actually the back and the tail of the bear. If you want to see the rest of the bear, you sort of have to look ahead of the pan of the Dipper for the head, and then look down below for the legs that end in little sets of 2 toes. You can imagine there at the ends of the paws. Let's see if I can get the all my star information off here. You probably know that if you take the 2 stars at the end of the pan and shoot over here, you can find Polaris, the North Star, that star used by navigators for millennia. It's the star the entire sky appears to rotate around as the Earth rotates on its axis. My astronomer friends love pointing out that if you go the other way and use the handle of the Dipper or the tail of the bear, you can create an arc in the sky and arc over to Arcturus, the brightest star in the constellation Boötes, the herdsman. And I always like pointing out that, you know, if you see a herdsman there in the sky, good for you. I don't, but at least I can see a bit of another, shape here. I see a diamond. This time of year, if you want to think about that as a baseball diamond, that might be appropriate. I see it as a kite there, and the end of the kite having its tail coming down and ending in that decoration there with that red star Arcturus. And if we move around,
We see an ice cream cone.
Yes, an ice cream cone. That's what it's too. You see, it is hot out there in Arizona, and yep. We move around here to we see the bright blue star Spica there in Virgo, and that'll be a good reference point for a couple of questions for our guest in a little bit. As we move on around, we find another star, very, very different than the bluish Spica. We find the very red Antares. It's appropriate to point out it's red, and its name there with Antares literally meaning the anti or the other Mars, because Antares, being here in part of the constellation Scorpius, the Scorpion, lies there with the other zodiacal constellations and the planets on the equator of our solar system called the ecliptic that runs here across the sky. And so at times, Mars itself is there very close to Antares. And so you have these 2 red objects that are very, very similar to each other. So there's Mars, the red planet, and its anti-Mars being the star there, Antares, that is much, much, much larger than our sun. And we'll probably talk about that in a little bit as well. As you move around to the southeast, we can find Jupiter and Saturn that have risen there above the horizon. I encourage you to take a look at those on a clear night this time of year. And with binoculars, you can see the 4 Galilean moons of Jupiter. It's 4 big moons that are really kind of planets in their own right. And Saturn, if you certainly can see the rings with binoculars or a good telescope, you might also be able to make out its largest moon, Titan, the only moon out there with a permanent, stable atmosphere that is actually a little denser than our own and made of largely nitrogen like our own, but with methane rather than oxygen. So not a nice place for us to breathe, but may represent some of the early chemistry that we had here on our planet. As you move around to the east and to the northeast, this is the direction that maybe some of you were out some days ago looking for those Perseid meteors. The constellation Perseus is right over here. And this is the radiant of the shower. And so even now, you might want to look that direction and find a few of those meteors that will continue to appear in the night sky for days and maybe even a week or so into the future. Now, if we move up at this time of year, we find another asterism. This time, rather than a pan making a Big Dipper, we find a giant triangle. This triangle is called the Summer Triangle. It's not part of a constellation. Instead, each bright star is the brightest star in its own constellation. Here with Vega and Lyra the Harp, Altair, the eye of Aquila the Eagle, and Deneb, the tail feathers of Cygnus the Swan. And if you can't see a harp and an eagle and a swan, I don't fault you. And that's another reason we have tools that we can help you with that. And if you still can't see with the lines there, those patterns that the ancient astronomers of Greece and Rome could see in the sky, we can put a little artwork up there to help you along. So if we go on into the night, we can also see just after midnight, Mars rising. And early morning, we can look to the northeast to find Venus above the horizon. But I'm going to come back here to our guests. Again, we are joined by Gerard Van Belle from Lowell Observatory. And he is, I believe I'm right, he received his doctorate from the University of Wyoming and has served as director of Lowell, but is currently in charge of a project and facility that's fascinating that he's going to tell you about. That is called the Navy Precision Interferometer. And if you don't know what an interferometer is, other than the fact it has a cool name, I'm sure he's going to tell you about that. And just like always, this may be a little weird. I don't know how this is going to work with ways of being able to communicate with us. But Jim, if you are out there and you get any questions via Facebook or anywhere else from the audience, we'll pass those along. As well as, I'll just tell everybody, we will make this available as always. It's available for you viewing into the future. And if you have any questions about anything you hear, please pass those along to us. We'll do our best. If I can't answer them, I'll be sure to send an email to Gerard and his colleagues, and we'll get answers for you. So again, thank you so much for being with us and your patience, Gerard. And I'm going to turn it over to you and just, again, tell us a little bit about what you do with Lowell and this, wonderful world of interferometry.
Well, thank you for that introduction. I really appreciate it. I've been at Lowell now for about 9 years. I actually have not been the director of Lowell. I've been the director of the Navy Precision Optical Interferometer. During my time at Lowell, the director has been Jeff Hall. And I've been at Lowell working on this interferometer called NPOI, the Navy Precision Optical Interferometer, among other projects. And what it is a very interesting telescope. It's a telescope made of telescopes. I can actually show you a picture of that if you want, if I can grab the screen share right here. And if you enable that, I'll go ahead and show my image.
Yeah, I'll make sure that you can get in here. Let's, I think you can, yeah, we'll be able to do that. And if you try that more time, you should be able to get that up.
All right, here we go. Yeah. And so this is what our interferometer looks like. It is big enough that you can see it very easily on Google Maps like this is. I'll point out that there are, this is a site called Anderson Mesa, which is about 10 miles outside of Flagstaff, and a very easy drive for me to go out Lake Mary Road and go visit this. And the observatory has operated telescopes at this site since the early 60s. This was our first dark sky site. The Flagstaff area is an international dark sky city. And so I can go out on my front porch and actually look up and, looking into the night sky, I can see things like these constellations that you were calling out earlier. But if you look at Deneb, the tail of Cygnus the Swan that you pointed out in the summer triangle, Cygnus is flying along the Milky Way, and that's always a nice constellation to see, because when you look up from Flagstaff, you can actually see the Milky Way, which is pretty cool. But nevertheless, we wanted even darker site already starting back in the 60s, so we opened up this site. We even have another site now that's even further away from the city, where we have our 4.3 meter Lowell Discovery Telescope. But here on the Mesa, we have these facilities. If you look on the kind of center left of the image, you'll see two round domes There's a third one kind of below them just as well. The bigger of the two has an interesting story there. It's the Perkins telescope. It's a 72-inch telescope, and when it was first made, it was the third largest telescope in the world, and it was put in an observatory in Ohio, and it lived there for about the first 30 or 40 years of its life until somebody finally looked out the window and said, you know, the weather here is not very good. And so at that time, it was moved to Flagstaff and is up on the mesa with the rest of us. But starting in the 90s, this new technology called interferometry started to be used in the visible. For about 30 or 40 years prior to that, the field had developed where we built telescopes made out of many telescopes in the radio. And if you've ever watched the movie Contact, you have Jodie Foster sitting out there in the hood of her car with the headphones on, and you can see all these antennas going off in the distance. That is the Very Large Array, which is a very big telescope in Socorro, New Mexico. That's about 6 hours east of here. And that facility is a radio interferometer. And in the radio, interferometers, for various technical reasons, are easier to build. And it's only in the 90s, over the last couple of decades, that interferometers that use optical telescopes that use light, like what our eyes can see, have been put together. And so this NPOI, the Navy Precision Optical Interferometer, is one of them. And these Y-shaped arms each extend about 750 feet to the north, the east, and the west. And along these arms, we have small telescopes, individual telescopes, that capture light, and they put it into a pipe that has had all the air sucked out of it, a vacuum pipe. And we relay that light all the way to the back end to this laboratory, where we then very carefully weave the light back together. And we're able to synthesize an image as if we had a telescope equal to the size of the separation between the telescopes. And so the greatest extent is 437 meters. That's about 1,400 feet from tip to tip to tip. And that basically lets us have a telescope with extreme resolving power and extreme capability to see very, very fine details in the sky. And I've been using telescopes like this, arrays of telescopes like this, over the course of my career to do interesting things, to measure things that nobody else has been to measure before. And so one of the things that I've done is, if you look at all of the stars for which we've had a direct size measurement, all the stars for which we just don't see as a point of light. So for all these stars that were being shown in our little walkthrough in the virtual planetarium just in the last few minutes, every single one of them, if with a conventional telescope, a regular telescope that's just made out of a single lens or a single piece of glass, if you zoom in as much as you can, you're still just going to see a point of light. And what I work on is being able to peel it apart and actually see it as a disk. And so the first thing you can do is just measure the sizes of sizes of stars. And that allows me to actually take the temperature of these stars and directly measure these things rather than kind of indirectly measure it. One of the things astronomers have done for a very long time is be very smart about doing indirect measurements of, well, if you look at a blue stars are very hot, and you look at red stars are kind of cool compared to the blue ones. Our sun is kind of in the middle in color, so it's kind of in the middle in temperature. And these are all very indirect ways. But if you actually measure the size of the star and then measure its brightness, you get the temperature for free. And so one of the things that I have done over the course of my career is measure the sizes of stars that are evolved. And so on this plot I've shown here, we have along the vertical axis, we have the intrinsic brightness of the star. So going to the top is the brighter stars, going to the bottom is the dimmer stars. And I've called this out as the intrinsic brightness. So you put in a correction for if they're near or if they're far, because a nearby star will just appear brighter than a distant star. So basically you make a correction to make it seem as if all the stars are exactly the same distance. What's the intrinsic brightness? And then along the x-axis, along the horizontal axis here, is the temperature. And astronomers plot these things in kind of kooky ways. They put the cool stars on the left and the hot stars on the right. And what's interesting about this diagram is you get this kind of avenue going through the middle from the upper left down to the lower right. And astronomers call this the main sequence. These are all stars that are in their middle age. And the curious thing is that when stars get to their old age, they actually start to wander off of the main sequence and they move up to the upper left over here. And sorry, upper right-hand side over here. And they swell up in size and they cool down. Our own sun will do this in about 4 or 5 billion years. It will run out of fuel in the center, and in kind of a desperate panic to try and keep itself alive, it'll actually burn other fuel faster, and it'll swell up to be a red supergiant, a red giant star, and it'll get large, it'll get cool, and then this will last for, I think, about 100 million years, and then it'll puff out. It'll actually die, despite the fact that it's doing its best not to. And so these stars that we actually see currently in this upper right-hand part of the plot, these are the giant and supergiant stars that have started to run out of fuel in their center, and they've puffed up in size. And so most of these stars inside the red dotted line who have had their temperatures and sizes directly measured, those have mostly been done by me, actually. That's a principal area of my research. And so I've done this size measurement. Now, if you are getting good at this game as far as using these arrays of telescopes, not only can you get a lot of resolution to just kind of measure the size of a star to, basically grab a ruler, which I don't seem to have in my desk drawer here, and kind of paste it on the sky and see the size, but you can actually start to make pictures of the stars as well. And so a game that you can play is actually zooming in and looking at images of these stars. And so the upper right here is the star Altair, which you called out in your little tour of the night sky as part of the summer triangle. If you zoom in on Altair with one of these sort of telescope arrays made of telescopes, and you're able to actually see it for what it is, you'll see that it is a object in the sky, and it's actually, despite the fact you might expect the star to be round, it's actually not quite round. It actually looks a lot like a beach ball that you've squished in your hands, and the edges have popped out. And the reason for that is that Altair spins. It spins very fast. Our own sun, which we can see in the sky, is pretty round. It rotates about once every 30 days in a very stately manner. However, Altair is actually twice the size of our sun, but it's spinning every 12 hours. It's spinning so fast, it's trying to rip itself apart at the equator. And so the equatorial region of the star, which, if you can see my mouse cursor, is kind of along here, it's actually stretched out because centripetal acceleration is trying to pull material away from the center of the star. And that only applies at the equator. At the poles actually kind of squish down because they're not rotating very fast. They're stuck at the poles. But the equator stretches out. It's a lot like if you're on a merry-go-round and you're kind of hanging on at the edge of the merry-go-round and somebody pushes it real fast. And the merry-go-round makes you feel like you want to get thrown off at that point. And so that's centripetal acceleration. And there are some sorts of stars which actually show that effect. And so this is a whole kind of gallery of these sorts of stars that we've taken pictures of that look like that. Interesting effect is that the heat of the star, the energy of the star, is coming from the core, and the distance from the core to the pole is shorter than from the core to the equator. And so temperature is falling off with distance from this thermonuclear reactor at the core. And so the poles being closer, the poles are hot and the equator is cool. And you'll actually see that you get these hot spots on the poles, like this thing right here. And then the equatorial region is quite a bit cooler. So that's the second thing that I've participated in and done that's been kind of my claim to fame in astronomy. I'm going to call out one last thing quickly here, is something I have not done, but I want to do with these interferometers, which is we've been seeing and finding more and more stars that have planets. And we've been finding a few of them where we have this chance alignment where the orbit of the star around the planet, sorry, the planet around the star, happens to actually fall between our line of sight between us and the star. And so it's very hard to see the planet. They don't give off a lot of light. They only are really reflecting light from the star. But an interesting game you can play is if you have it line up just like this, if you're making an image of the star repeatedly over the course of time, you can actually, not seeing the planet, but seeing the not planet go in front of the host star, you can make an image of this transit event. And you can make, if not an image of the planet, but an image of the shadow of the planet over time. And it would look a lot like what we have here when about 10 years ago, we happened to have it where in our own solar system, Venus happened to line up between us and the sun, and we could make a little image of the shadow of Venus passing between us and the sun. And the idea is to do that with one of these arrays of telescopes that have the very powerful amount of magnification to see very fine details. It's that these sorts of arrays are like if you have a quarter. If you in Atlanta were to look at this quarter in my hand here in Flagstaff, that's going to be the apparent size of Altair. The apparent size of that star Altair in the sky is about this quarter as seen from your location in the Atlanta area versus this quarter here in Flagstaff. This trick I want to do with imaging the shadow of a world going around, that's actually, you have to go to smaller stars, and it's a lot more like trying to image George Washington's eye on the face of the quarter during that event. And so with that, I'll go ahead and come back to the regular feed here, and we can talk about stellar evolution and any questions you might have.
No, I think because we have a pretty diverse audience out there, and you've talked about the different temperatures of stars. I mean, just in general, when you look up in the sky and we see something like I mentioned with Spica, and then you see Altair or you see Arcturus, just what is the range of differences in those stars? What do they, as you mentioned, those colors? Again, what do they mean? What's the range in what we see out there in our galaxy, and what does that mean about how those stars kind of got going and where they're headed?
So with the cooler stars, they are reddish because they're giving off a lot of their energy towards the red part of the spectrum. And the temperatures there are about 3,000 Kelvin. The astronomers use the Kelvin temperature scale. Roughly twice that is what you'd get for the temperature of the star in Fahrenheit. So the cooler stars are about 6,000 Fahrenheit. Our sun is a little bit bigger, and so it's a little bit hotter at about 5,000 or 6,000 Kelvin. And it actually gives off an equal amount of its light in the blue and about an equal amount in the red. And so it appears kind of whitish to us, actually. Even though the peak is in the green, it's kind of, everything's kind of muddled on out. That's actually kind of unsurprising from an evolutionary standpoint, that our eyes are optimized for the light that is in our environment, which, so we got pretty much a pretty flat response from our detectors, our eyes, across the available light. Even hotter stars, something like Spica, is going to be a blue looking object. And these are going to be things that are 10, 20, 50,000 Kelvin in temperature, so very, very hot. And an interesting connection there is that for those stars along the main sequence, for those stars that form the majority of stars kind of in the middle of their life, as you go from the coolest stars up to the hot stars, you actually not only are increasing in temperature, you're increasing in mass. And so the smallest stars are the coolest stars. They range from about half to a tenth the mass of our sun. And then our sun, again, is in the middle. And the biggest stars are 10 to 20 to 50 times the mass of our sun. And they tend to get bluer and bluer and bluer as they get hotter and hotter and hotter. An interesting little bit of demographics there is that the very coolest stars are the faintest stars, but they're they're really kind of the vermin of the sky. They're the ones that make up the majority of the objects in our universe. They don't we don't see a lot of them because they're faint. But about 75% of the stars in the sky are actually smaller than our sun. When you look up into the sky, you actually see kind of a whole menagerie of stars because even though the bluer ones are rarer, they are brighter and hotter, and so you see them from a greater distance. And so even though they may be less populous throughout our galaxy, they make themselves noticed, and so you see them in the sky.
And speaking of making yourselves noticed as stars, and our feature presentation tonight is called "The Secret Lives of Stars," and so as you hopefully have heard, Gerard is literally one of the paparazzi of the stars. He has these developing these ways of really this is like the real paparazzi, like diving literally into the bedroom of the Hollywood stars, trying to get that that picture that's ever and ever more detailed and revealing. And one of those stars that has tried to put on a show for us back starting last fall, you can take a look at in the early morning sky right now. I'm going to hop back to Stellarium just for a second, and so we can take a look here. This is about 5 o'clock in the morning if you happen to be up, and you're looking out toward the east, and you'll see Venus, as I mentioned, and our moon is out there right now as well. If you see those bright objects and look just a little to the south, you'll see a bright red object, and you'll actually see another red object above that. This is Aldebaran and Taurus, the bull, up at the top. But down just to the south of Venus, you'll see Betelgeuse, which is the right shoulder of Orion the Hunter, and that you can recognize by the 3 stars of the belt there. And Betelgeuse is a red supergiant that, as I mentioned, tried to give everybody quite a show back last fall and through the winter. And I'm going to ask Gerard if he can talk a little bit, because I know we have a lot of amateur astronomers out there who are paying attention to this. And just what is the current thinking of if you could describe a little bit what happened there with Betelgeuse and why it happened, I think that would be kind of fun.
So Betelgeuse is a very interesting star. It's a big star, but it's also a very, relative to its overall life, it's ready to die. It's getting very, very close to the end of its life. And what happens with big stars that are, say, 8 to 10 times as big as the sun, when they get to the end of their lives, they violently explode in something called a supernova. And Betelgeuse is basically ready to pop. And it's gonna pop any day now in astronomical terms, which in human terms means any time between tonight and the next 100,000 years. So, who knows when it's actually going to happen? But what's interesting about this is that it's made it a object of some interest, since it is actually, from a galactic standpoint, quite close by. The galaxy is about 100,000 light years across, and Betelgeuse is about 600 light years away. And so it's really kind of on our doorstep. And were it to actually go supernova and kind of have this last dying burst of energy, it would light up as bright as the moon. And so you could see it in the middle of the day, actually. But it has not done that yet. But an odd thing happened starting last fall, which was the brightness of Betelgeuse started to dip. It actually became, 10% less bright, and then 20% less bright, and then it really bottomed out at about kind of a third to even half as bright as it usually is. And we didn't know why. And we're still trying to disentangle that, the astronomers in the astronomical community. But some of the popular thinking is, along the lines of a couple of explanations. One of which is when you look at any random star, and our sun is the best example, and you look at it closely and you look at its surface, you'll see spots on the star. There are areas on the star which look black. They're actually not black. They're still quite bright, but relative to the surrounding areas, they're not as bright. And they are just areas where they happen to be a little bit cooler. And on our sun, the diameter of these spots is pretty small compared to the overall disk of the sun. 10%, or not even 10%, probably 1/100th of the diameter of the sun is the size of these spots. Now, on Betelgeuse, because of how it is structured and how it moves energy through the star from the core that's generating energy out to the surface, the spots are actually much, much larger. Not 1/100th the diameter of that star, but more like 1/4 of the diameter of the star. And so one explanation has been that you just happen to have a pretty big spot that rotated into view on this body and made it appear as if the star was less bright. A second explanation is that stars like this that are near the end of their life, the outer parts of their surface are still quite hot, still 3,000 Kelvin, but it's actually just cool enough that the material that makes up the star, it's principally hydrogen and helium in a gaseous form, but a star like Betelgeuse is also kind of coughing up from its core extra junk, soot and ash and stuff that's left over from its thermonuclear fires. And so you get carbon, you get nitrogen, you get oxygen. The carbon in particular is very good at making soot, at basically making dust. And that gets coughed off the star from time to time. And it's thought that maybe an explanation was that Betelgeuse happened to have belched up a particularly big clot of dust at that time, which blocked some of the light that was coming off the star. And so since that time, Betelgeuse has come back up in brightness. Given that this was actually a pretty notable event and pretty substantial event and how much light it dimmed it, some people were saying, well, maybe this is some kind of harbinger that it's going to go supernova. That's probably not the case. I would love it nothing more if that were to actually happen, because that would be so cool to see something like that during our lifetimes. It's very rare to have a supernova go off that you could see yourself in the nighttime sky, much less in the daytime sky. I think the last time that happened was about 500 years ago.
Well, that's kind of where I wanted to end with the questioning this evening, is just in terms of all the observational time that you have spent looking out to the galaxy. What is the kind of neatest thing that you recall seeing or that you've been involved in discovering?
So I'd have to say our work with observing Altair and seeing how it is rotationally oblate and stretched out of the middle and has the temperature stratification of the surface. That's been pretty special, because that was a effect that was predicted 100 years ago by a fellow named von Zeipel in 1924. And we were the first ones to directly see it. And it was a result of this new technology and this new kind of telescope that we built, and being able to see things in much greater detail than anybody has before. And so that was very exciting. And there have been other times in my career where I get to do that, which is just a lot of fun, where you're the first person to see this thing and you get to share it with everybody. That's cool.
And I'll just conclude now, thanking Gerard for his time being with us this evening, his patience as we had experienced some technical difficulties, and also the patience for all of you out there, and bearing with us as we had to sort of shift gears to, this kind of welcome to the new world here. And as we get into the school year, many of you are experiencing this more and more, where you have to sort of divert off one way and then duck and dodge, go the other way, just to make sure all the technology is doing, what we want it to do. But I would also mention with Lowell Observatory, if you haven't been there, when things do get back to normal, please make a point. If you want a very pleasant place to vacation, you can't beat Flagstaff. I did my undergraduate work at Arizona State and got to spend quite a bit of time on the Colorado Plateau to get away from the heat of the Phoenix Valley. But it's a beautiful area, and right there in the middle of it are two marquee places for those in my business and Gerard's business with Lowell Observatory and the United States Geological Survey's astrogeology branch. And it is not only the research that goes on there currently, but the history in looking out into our galaxy and the solar system in particular. With you can't not mention that they have the telescopes that Clyde Tombaugh, or the device Clyde Tombaugh used to discover Pluto. Yep. And because of that history, they're one of the groups of astronomers out there who are kind us planetary guys with in making sure that Pluto is gets all the glory that Pluto has always deserved. So we always appreciate that about Lowell and its incredible history. But yeah, if you are in the area in the future here, please make a point of visiting them. They have an incredible installation that is incredibly friendly for the public in normal times, and just is a beautiful campus to be on. So
we've been very fortunate to host so many visitors on our campus, and we just opened up our new Godo Observatory, where when we open up again, you can come and look through telescopes at the night sky from sizes of 8 inches up to 31 inches in size. And before that happens, we have a big online presence, and you can find us on YouTube as well for virtual experiences as well before then. So thank you for having me. I really appreciate that.
And I don't know if you know this, we have, and I'll remind everybody here, we have not only our huge planetarium, but our 36-inch reflector, which is the largest of that kind on this side of the country. And we hope to be able to, we're still working on trying to get a way of getting cameras attached to that so we can share some of that view with you, even in these sort of extraordinary times. But we hope as soon as we can manage it to get people back there for both the observatory and planetarium. But for this evening, we're going to switch over here again. Thank you, Gerard. And now we're going to hear from the Captain Picard himself with the Patrick Stewart narrating Secret Lives of Stars.
Most people around the world know the name of a famous star, a Hollywood star. Very few people know the names of the real stars, the stars in the sky. The media tells us everything about the lives of Hollywood stars, but the stories of the real stars are ever more interesting, more exciting, and more relevant to our lives than most of us imagine. Welcome to the fascinating revelations of The Secret Lives of Stars. A night ends and the stars fade. The sun rises as our planet turns us toward it. Sunrise, we say, but it's actually starrise. The sun, at 150 million kilometers distant, is the nearest star to us. Its light takes 8.5 minutes to reach us. It's the light and heat from the sun that allows most life on Earth to survive. Like all stars, it's a giant nuclear explosion releasing vast amounts of energy. The balance between its own gravity and this explosive force shapes it into the disk we see in the sky. Seen in close-up through the eyes of various spacecraft, its explosive nature is very obvious, as is its true size, 1.4 million kilometers across. That's big enough to put 1 million Earths inside. The surface temperature is just over 5,500 degrees Celsius, but at its core, where nuclear fusion occurs, it's around 15 million degrees. The sun is big and bright because we're so close, but what would it look like from the distance of the next closest star to us? Let's do a little star trekking to find out. Using this fantasy warp factor, we've traveled 275,000 times farther than the Earth is from the sun. We're at a multiple star system known as Alpha Centauri. If you know the star patterns, the sky doesn't look all that different than it does from Earth. There's the familiar W shape of Cassiopeia. And here is one extra star. That star is our sun. It's just an ordinary star among the thousands of others in the sky, and it's now 41 million kilometers, or 4.5 light years away from us. Let's boldly go again. This time, we're hundreds of thousands of light years away from the Earth and Sun. We're looking down at the Milky Way, our galaxy, the collection of about 200,000 million stars to which our sun belongs. Our star is impossible to pick out. We know it's about 2/3 of the way out from the galactic center. Just as a forest contains old trees, saplings, dead wood, and new seedlings, so a galaxy contains all types and ages of stars. In some places, new stars are being born. Other older stars are living out their lives, often in groups. And there are remnants of once mighty stars that are no more. You might ask, how do we know so much about these very distant objects? A rainbow holds a clue. Rainbows form when sunlight passes through drops of water in the atmosphere. The water breaks up light into its individual colors. Visible light is just a tiny part of the radiation we can observe from distant stars. The spectrum. Studying a star's spectrum can reveal many of its secrets. In this manner, we know that stars vary considerably both in size and temperature, and that these traits are related to a star's composition, age, and most importantly, its mass. Massive stars have short lifetimes, while the least massive have amazingly long lives. Live fast, die young is the rule here. Most numerous are stars smaller and cooler than our sun. Some can live for trillions of years, consuming their nuclear fuel, hydrogen, very slowly. Our own sun, larger, hotter, and brighter, will use up its fuel over 8 to 10 billion years. This star named Sirius, with twice the sun's mass and 26 times brighter, will last only hundreds of millions of years. It's the brightest star in our sky, but only because it is a mere 8.5 light years away. This star, Rigel, is nearly 100 times further away, has 20 times the sun's mass, and is 40,000 times brighter. It will live only for tens of millions of years. Some stars with lifetimes of only 1 million years or less could be up to 150 times the mass of the sun. Probably the biggest well-known star is Antares, a red giant which, if placed in the solar system, would engulf all the planets as far out as Jupiter. It's a star near the end of its life, a stellar time bomb, a future supernova. From Earth, Antares is a brilliant red star in the constellation of the Scorpion. It lies in the direction of the center of our Milky Way galaxy. Seen through the eyes of giant space telescopes, the vibrant central region of our galaxy contains vast clouds of cool gas, dust, young stars, older stars, and the debris of dead stars. This is the still expanding remnant of a star that exploded as a supernova thousands of years ago. In Earth's sky, it covers an area as wide as 80 full moons. This more compact remnant is of a massive stellar explosion that occurred 400 years ago. A supernova is the explosive death of a star. Its fuel consumed, energy creation stops. The star collapses, then rebounds to blow itself to pieces. It's supernovas that form the heavy elements of the universe, elements needed for our planet, our technologies, and our bodies. If the star is not massive enough to form a black hole, a tiny spinning neutron star forms, just a few tens of kilometers across. It has tremendous gravitational and magnetic fields. As it spins, we get a rotating beam of radiation, a series of pulses, hence the name pulsar. This star, Rigel, is a prime candidate for self-destruction relatively soon as stars go. It's a supergiant about 800 light-years away and 70 times the width of our sun. From an imaginary airless world hundreds of million kilometers distant, Rigel would be a breathtaking sight, as brilliant as 40,000 suns. Closer now, the view is awesome. Observations show that Rigel appears to be billowing great amounts of its material far out into space. This continuous loss of its mass just might prevent Rigel from exploding and enable it to end its days as a tiny white dwarf star surrounded by a vast nebula. So while it is still there, why not catch it in the famous constellation of Orion? This churning mass is Betelgeuse, a red supergiant star second only in diameter to Antares. Betelgeuse also is in the last moments of its life. It could explode any time between now and the next few million years. When this happens, Betelgeuse will become nearly as bright as the full moon. Betelgeuse is located opposite Rigel in the shoulder of Orion. A cloud of gas in space is called a nebula, and the one in Orion is the brightest in our sky. It's the home to hundreds of young stars, most just a few million years old. Radiation from these hot young stars causes the gas to glow and sculpts the canyons and towers within the cloud. Many stars here are surrounded by dark disks of material, perhaps early planetary systems. From a planet within this stellar nursery, brilliant young blue stars would dot the sky. They would shine like celestial gems against the surrounding gaseous clouds. 5 times more distant than the Orion Nebula, this is the famous double cluster in Perseus. The clusters are about 300 light-years apart. These are young stars, no more than 14 million years old. In 100 million years, they will open up more and could resemble the famous Pleiades star cluster, better known as the Seven Sisters. From some of the youngest stars, we move to some of the oldest, far older than even our galaxy. When the Earth was forming almost 5 billion years ago, these stars were already 7 billion years old. These oldest stars are found in globular clusters, the spherically shaped collections of stars that orbit outside the center of our own galaxy and many others. They contain many densely packed millions of stars. From an imaginary planet in a globular cluster, perhaps 13,000 stars would dominate the sky. Planets here are extremely rare. Stars have not exploded to form the heavy materials needed for planetary formation. In the constellation of Auriga lies an intriguing star, Epsilon Aurigae. As seen from Earth, every 27 years, a strange eclipse occurs. The star dims and brightens over a 2-year period. From nearby, it must be an amazing sight as a huge dark disk, 800 million kilometers across, passes in front of the central star. The Spitzer Space Telescope revealed its secret, a huge dark disk surrounding another orbiting companion star. The disk is apparently composed of very small particles about the size of a grain of sand. This material may have accumulated from the parent star that is actually dying, even though it's shining as brightly as 140,000 suns. Stars whose light output changes are called variables. Algol in Perseus was the first eclipsing variable star to be discovered. On Earth, its constant winking led to the name the Demon Star. Measurements of its regular changes led to the discovery that it is actually 2 stars, regularly passing in front of each other as seen from Earth. So close are these stars, about 8 million kilometers, that one is pulling material away from the other, and the whole system is active with radio and X-ray flares. Unlike Algol, Mira is variable because it actually changes in size. It brightens and dims by a factor of 1,000 over an 11-month period. Later in its life, our Sun will behave like Mira, both ending as tiny white dwarf stars, even smaller than the Earth. As it moves through space, Mira is losing material that forms an immense gas trail over 14 light-years in length. It has a distant orbiting companion around which planets may be forming. Although no Earth-like planets have yet been discovered, hundreds of planets have been found orbiting nearby stars. It seems that star and planet formation go hand in hand. Planets in distant galaxies are too far away to be detected, but signs of star formation are easy to find. In the October skies from Earth, we can see, even with the unaided eye, the nearest big galaxy to us, Andromeda. Perhaps twice the size of our own Milky Way, it takes 2.5 million years for its light to reach us. Close images of the Andromeda Galaxy clearly show the great clouds of gas and dust where stars are forming. In this small galaxy, the clouds with glowing pink hydrogen gas are easily visible. In galaxies near and far, these telltale signs of star formation can be found everywhere, as can stars in every stage of their lives. These observations show that our ideas about the secret lives of stars hold true throughout the visible universe. We're back in our own galaxy now, looking at the biggest star-forming region near us. About 1,200 light-years from Earth is this giant cloud of gas, dust, and young stars. Astronomers call it a molecular cloud. It covers a large part of the area around Orion. This cloud, 5 times farther away than the Orion Nebula, is bursting with the light and energy of young stars hidden within. This immense cloud could stretch from our sun to the nearest star. From afar, these clouds look dense, but in reality, they are almost a vacuum, and so can be easily pushed and pulled. The exact mechanisms that give birth to stars are not fully understood. It's believed that nearby exploding stars have a role to play in this process. Their shock waves are thought to trigger the gradual compression of the hydrogen-filled molecular clouds, pushing them closer together. Over time, as gravity collapses the clouds even more, their core temperature and pressure get so high that nuclear fusion occurs. In this process, hydrogen atoms fuse to form helium, releasing enormous amounts of energy. Often, these young stars shoot great jets of material into space. At some point, the outward explosive force of fusion and the inward pull of gravity balance each other, and a star is born. Cooler materials around the young star then start clumping together to form the bodies we call planets. They differ from stars in that they don't generate heat and light through nuclear fusion. They only reflect light from their parent star. Here, the Hubble telescope reveals a newly forming star system in this 3.5 light-year long finger of molecular clouds. The jets from a young hidden embedded star reveal its presence. After millions of years, such star-forming regions would look like this, the Rosette Nebula. Hot young stars emerging from the dusty, gaseous cocoon in which they first ignited. Multiple star systems are very much the norm. Some make the most unusual scenes in the universe. This twin system, in the constellation of Lyra, has 2 stars orbiting so close that their mutual gravity has distorted their shapes. Material exchange between the stars forms a complex spiral, winding around the companions and swirling through space. But not all companions get along so well. A few years ago, a dim star suddenly became 600,000 times brighter, its light gradually illuminating nearby gas clouds. This was a stellar collision on a Hollywood scale. We had just witnessed a real cosmic smash-up as 2 stars plowed into each other with brilliant results. In certain systems where material is being pulled off one star onto the surface of another, massive nuclear detonations can occur. So, let's move to a safer distance. This looks like the scene of a stellar detonation, and although this is the ghostly shroud of a dying star, it is not the result of an explosion. It formed slowly over many tens of millions of years. Speeding up time over the next few billion years, the sun will change as the nuclear process in its core alters. Gradually, it will swell up, perhaps getting up to 150 times bigger than it is today. It will spread more and more heat through the solar system. Ice worlds will melt, and the atmospheres of the giant gas planets may boil away. Earth's oceans will vaporize, and our planet will be transformed into a broiling desert. Fortunately, we will have a few billion years to prepare for this, but it will certainly be the end for our blue planet. All over the heavens, we can see the remnants of stars like the Sun. Called planetary nebulas, these spectacular formations are made by the gases that once formed the star's atmosphere. Immense stellar winds blast much of its outer atmosphere into space. In the center of each, a small hot star, a few thousand kilometers across, what astronomers call a white dwarf. It's all that remains of the original star's core. In the last few billion years of its life, the dying sun will transform the region of space surrounding it. Outflowing gas will form a spectacular glowing cloud, a stellar shroud of immense proportions. Deep inside will be the remnants of worlds we call the solar system and a cosmic ash ball that was once the sun. The life of our star will end, not with a colossal bang, but with the creation of a magnificent stellar tomb, a fitting monument to the star that gives us life. Fortunately for us, the death of our sun is billions of years away. We have many more sunrises and sunsets to enjoy. A sunset is simply the Earth turning us away from our star. Sunset gives birth to another night, another chance for us to peek at, to explore, and to marvel at the secret lives of stars.
And thank you again so much for joining us this evening. Again, thanks to Gerard Van Bell from Loeb Observatory for being with us. And thanks to all of you for your patience with our technical issues this evening. I hope everyone enjoyed the program. We will be back. We'll try to be back with Facebook Live next Friday evening at 7 p.m. But now, those of you who have been joining us regularly, you know that if anything happens, we'll hop over here to YouTube. Will be interesting to find out what that glitch was about tonight. We are happy to continue to bring you the programming, and we'll continue to do this, as I keep saying, for as long as we need to, and maybe beyond. We've had serious discussions about even when the pandemic ends, of continuing some version of this program into the future. It's a great way to have some of the guests like Gerard with us, for our community to hear more in depth about what my science colleagues out there in the world do. And it's a real pleasure to be here with you every week, and I look forward to continuing that into the future. We will probably, right now, the plan is for next week to sort of turn back toward Earth with the dynamic Earth. And we'll probably be here, try to have some climate and meteorology folks with us. So that's the plan right now. You'll hear more about that probably on Monday if you're paying attention to our Facebook site. And again, have a wonderful weekend, and everyone stay safe and healthy, and look forward to seeing you next week. Good night.